Okay, let's start then. Well, thank you all for joining another lecture for Introduction to Computer Graphics. So last time we talked about textures. This time around, we are going to continue talking about textures, but we're going to talk about textures on the GPU. We're going to talk about textures as our GPU would see it, or the kind of texture-like things we can do on the GPU. That's going to be our main topic for today. So let's start with the main concept, right? So textures. So texture, you can think about this as like an image that you put on a 3D model, right? So that was a very minimal description of what a texture is. Textures are actually way more broader than this use case, but this is a typical use case. This is probably the most common use case of textures. All right, so I have a 3D model and I put some texture on it, right? We talked about this last time in quite a bit of detail. But textures don't have to be just like a 2D image like this. They can be, imagine just one slice, one row of this 2D image. So that one row of that image could be a texture itself, which would be a 1D texture. And this is a 2D texture, right? So we can have 1D textures. It's just a row of pixels. You can think about them that way. Or I can have 2D textures, and both would be recognized by my GPU. My GPU has 1D textures and 2D textures. It also has 3D textures. So I can think of a 2D image like this, and you extend it in one more dimension, and you get a 3D volume. And that volume would be filled with texture samples. You can think about it like a series of 2D images, and that would be a 3D texture, and that would also be recognized by my GPU, right? So these are the kind of textures. When we say textures on the GPU, this is what we mean, either 1D, 2D, or 3D textures. Of course, in theory, textures could be 4D, 5D, however dimension you want. You don't want to go too high because the curse of dimensionality is real. That's a real thing. It's as you go up in dimensions, things get really, really bad. But 3D is okay, and we have 3D texture support on the GPU, so it's all good. We have also, we talked about this briefly last time, procedural textures. Now, when people talk about textures on the GPU, they don't quite mean procedural textures. But procedural textures are also supported on the GPU. So what's a procedural texture? It's basically a function, right? You give it some coordinate, and it tells you the value of the texture, some function. So what can be a function? It could be anything. You don't even need to express it mathematically. You can express it algorithmically, right? So here's an example of a procedural texture implemented on the GPU. So this is GLSL code for a checkerboard texture, right? So it's taking a vector, this is a 2D position. You can think of it as like a texture coordinate. It's taking a texture coordinate and it's forming some texture. Can you imagine what kind of texture this procedural texture would produce? Like what would it look like? So what are we doing here? The first line is we're subtracting the coordinate. We're subtracting the integer part of the coordinate from itself. So we're just taking the floating point part of the coordinate. And then based on the floating part of the coordinates, we're deciding between two colors, right? One of them is 100, which is red. The other one is 001, which is blue, right? So it's going to be alternating red and blue checkerboard. Yes, so it will look like something like this. Yay! Right? And it'll just go on forever. There's no end to this texture. So procedural textures, they are supported on the GPU. We just need to write the code for them, and they work. That's about it, right? But when we talk about textures on the GPU, this is not what we mean. This is when for a lot of people look at this and they say, "Oh, this is just a shader code." Yeah, it is shader code, and technically it is a procedural texture. But when they talk about textures, they actually talk about textures that are supported, explicitly supported by the GPU. That is, these are 1D, 2D, 3D textures, right? So when we talk about textures on the GPU, this is typically what we mean, even though procedural textures are also textures. And that can also be implemented on GPU. So, but this is what we mean. And I'm going to talk about how to deal with this. I'm going to specifically concentrate on 2D textures, although the stuff that I'm going to talk about is going to be applicable to 1D and 3D textures as well. All right. So first things first, let's start with texture coordinates. Now, last time I told you that I was going to talk about texture coordinates a little bit. So let me do that. Oftentimes when we talk about texture coordinates, people think about UV coordinates. So we have X, Y, Z in 3D, we convert it to UV. We don't call it X and Y, we call it UV because we want to call it something else because it's not the same as our XY coordinate in the world space or in the object space. It's a coordinate in some different space, in texture space. And we call it UV because we typically deal with 2D textures, right? So when we're dealing with 2D textures, you're going to have two coordinates, U and V. If we have 3D textures, it's going to be UVW. That's the, typically those are what we use for representing them. If we have a 1D texture, we only have U, we don't have V. So here's the thing. On the GPU specifically, we have UV coordinates and we have ST coordinates. UV coordinates, specifically, if you look at, for example, OpenGL specification, UV coordinates depend on the resolution of the image. Right, so U coordinate goes from 0 to width and V coordinate goes from 0 to height, right? So these are resolution dependent coordinates. ST coordinates are normalized coordinates. So these are resolution independent coordinates. So if I have a texture image like this, this bottom left corner is going to be 0, 0, 0, and the other end of it will be 1. The same goes for the T coordinates. So ST coordinates will be normalized, as we call it, so that it's going to be resolution independent. So I'm not saying anything about the resolution. So typically on the GPU, when we are providing texture coordinates, we are providing ST coordinates, right? We want to provide resolution independent coordinates. And then our GPU will automatically take those ST coordinates and under the hood, it will automatically convert them to the corresponding UV coordinates and do the texture filtering automatically, right? So all of that stuff is going to happen automatically. And we are going to provide these normalized texture coordinates. Now, according to OpenGL specification, these are ST coordinates, but pretty much everybody calls them UV coordinates. All right, so here's the confusion. When people say UV coordinates, they actually mean ST coordinates. But if you go in and look at OpenGL specification, UV coordinates they have a different meaning. It means these unnormalized resolution dependent coordinates. But that's not what people mean when they talk about UV coordinates. When they tell you UV coordinates, they actually mean ST coordinates. They don't mean UV coordinates, okay? But yeah, I had to tell you the correct thing based on the OpenGL specification. But these are just some random names that we came up with. I mean, this could be UV and the other one could be ST. But turns out when people define them, they call this one ST, the other one UV. But UV caught on, ST never caught on. So everyone's calling this one ST. Oh, sorry, this one UV. Nonetheless, when people talk about texture coordinates, call them whatever they want, they typically talk about normalized texture coordinates, right? They can call it ST, they can call it UV, they mean normalized texture coordinates. And the nice thing about normalized texture coordinates is that I don't need to know anything about the resolution of my texture. It's just my GPU needs to know to be able to do texture filtering. But I just give it an image, there you go, there's your image. I don't even care what resolution it is. I say, use this texture and here are the texture coordinates. And which is really nice because, for example, I can take my teapot model and I have my texture coordinates specified on my teapot model and I can put an image of whatever resolution I want and I'm still going to use the same normalized coordinates. right? So I don't have to change the mapping. I don't have to change texture mapping just because I want to use a different texture with a different resolution, right? So we almost always use normalized coordinates when we talk about texture coordinates. So that's the reason why when people say texture coordinates or UV coordinates, they almost always mean this normalized coordinates. And if you look at a texture image like this, width and height, they don't have to be the same. They can be different. But in this normalized coordinates, I'm still going to have 0 to 1 on in both dimensions, right? So yeah, the image will be always in this coordinate frame. It will be scaled to a square, right? Because there's going to be maybe non-uniform scale because of that, if your resolution is not the same in both dimensions, right? All right. Is this enough discussion about this very simple thing? So you'll remember that when you see texture coordinates, when I say texture coordinates, regardless of what I say, I can say ST, I can say UV, I can just say texture coordinates. This is what I mean. I mean normalized texture coordinates, all right? And when people tell you, oh, what are the UV coordinates? They mean normalized texture coordinates. But technically, UV means something else, according to the API specification. All right, let's move on. We're just gonna have these normalized texture coordinates. All right. So in the rest of this lecture, I'm going to talk about different things you need to do to be able to use textures on the GPU. Now, this topic is a little bit tricky. It's not difficult, but it is tricky because textures don't quite work the way you think they would. There's a little bit of complexity in there, or it's not complexity per se, but there's something really unintuitive when you don't understand how this system works. But when you understand how it works, it will make perfect sense, I'm hoping. So the whole point of this lecture is to make sure that you guys understand how GPUs look at textures and how to set it up. And once you understand how it is, you will know how to do this. We'll get there. So we're going to assume that our texture coordinates are going to be between 0, 0 and 1, 1. And of course, our texture samples are just points in this space. So notice that these samples are sort of close to the edge, right? Because there's a half a pixel distance between this edge of the texture to the closest texel here, right? And then 1 pixel spacing between these other texels. All right, so let's take this and move this image over here. All right, so here's my texture. By that I don't mean a texture with my face on. I mean it's just whatever. It's a texture. All right, so and this is at the 0, 0 point. All right, and this is the 1, 1 point at the end, at the corner of the texture. Now, the first question is, what happens if I specify a texture coordinate that is outside of this nice domain of 0, 0 and 1, 1? So if I pick a point that's outside of this square, what happens then? Well, it depends on what you want to happen. So that's what we call, like, texture tiling is typically what we call it, and there are different ways of doing this. For example, we can just say, if you pick a point that's outside of this region, then the texture color of that point will be just the color of the closest texel, whatever that is. So that would be what we call clamped to edge. Right? We would look something like this. So in this case, what's happening is that, you know, it's like I'm extending the texels, the border texels, right? So that's what clamp to edge is. And it's called clamp to edge because I'm taking a given texture coordinate and I am bringing that texture coordinates to the closest valid position between 0, 0 and 1, 1. All right, so that's basically clamping the texture coordinate. That's why it's called clamp to edge. Right. All right, so that's one thing I can do. The other thing I can do is I can repeat it. Actually, this is the default mode. If you don't specify anything, I believe GPUs will do this. So texture will just be repeated. And the way to compute this is fairly easy. You just look at the floating point part of you just remove the integer part of your texture coordinate, and you look at the remaining part. And right. So of course it could be negative and whatnot, so it goes to infinity. Alright, so this is the repeat mode. And there's also mirrored repeat mode. Yeah, this is what it does. I think it's fairly obvious what it does. Alright, so these are the different modes that we can do. Once you specify this mode and once you specify your texture data, all you got to do is to give the GPU the texture coordinate to sample, and that's it. Alright, let's get back to our GPU pipeline, right? So remember this, we feed in triangles on one end, they go through our vertex shader, and then our rasterizer, and then the rasterizer generates the fragments, and the fragments go into the fragment shader. So let's now assume that I'm going to need my texture in my fragment shader, because to be able to put that texture on my teapot model here, I will need to know the texture value for every fragment, right? So I'm going to be sampling that texture inside the fragment shader. So how do I send it to my fragment shader? It's not going to go through this pipeline. I'm going to send my texture directly into my fragment shader like so. All right, so I'm going to just figure out a way to send it to my fragment shader, very much like a uniform variable, right? We specify uniform variables. We can have uniform variables in vertex shaders and fragment shaders. Just like that, we're gonna directly give access to our textures inside our fragment shaders. So this is the tricky part. Now, this could be very easy, right? I could just specify a texture and I can just say, oh, fragment shader, there you go, this is the texture, and then I use it. It is almost that easy, but there's a little bit of extra tricky part in it that makes this setup a little bit difficult. And that's the whole point of this lecture, to make sure that you guys understand this tricky part. Because when you don't understand this part, like you can read all sorts of WebGL, OpenGL tutorials, you will see how this is done, but it will make absolutely no sense if you don't understand why this is happening, why there's a bit of complexity in sending this texture into my fragment shader. Here's why. There's a little bit of a hidden component in here. Very, very important, very, very valuable hidden component in here. I can't directly send my texture to my fragment shader. They go through what we call a texture unit. Now, a texture unit is typically an actual physical hardware unit that sits on your GPU. And this is a very valuable unit. We talked about this briefly last time. This is where my GPU is going to do texture filtering. Remember the bilinear filtering we talked about, or mipmap filtering we talked about? Yeah, and anisotropic filtering. All that stuff is going to be done by this guy. This actual existing physical hardware unit that will do my texture filtering. That's why this thing is very, very valuable. So because I don't want to do texture filtering in software in my shader code, that would be very expensive. I have actually this physical optimized hardware unit that will do the texture filtering for me, and that's going to be a lot more efficient. And the efficiency is very, very important, because a lot of times the cost of processing textures or sampling textures will determine your rendering speed. A lot of times that's going to be one of the most expensive parts of rendering. So it's very, very important. So the entire tricky part is sort of designed around this. But once you understand that this guy exists in between here, and I kind of need to send my texture to this guy, and then I need to send this guy to my fragment shader. Once you understand that this guy exists, you basically, the rest of it is not tricky anymore. I'm going to tell you exactly how to do that. But an important note here is that I keep showing that texture goes to the fragment shader. It doesn't have to. Actually, I can access textures in my vertex shaders as well. That's definitely possible, right? it happens exactly the same way. There isn't much of a difference, except that mid-map filtering becomes a little different. But it doesn't matter. GPU will handle that. You can just ignore that. There's a difference. You can access them in your vertex shader. You know what? Let's forget about that. Let's assume that everything is going to fragment shader. This is exactly where we will need our textures, right? So let's just take that part. My texture going through my texture unit into my fragment shader. You know what? I'm just going to call it shader. Doesn't have to be fragment shader. It's some shader that's accessing my texture. Okay, I mean, it's all good, but what if I want to access more than one texture? If I have just one texture, this is good, but what do I do if I have multiple textures? Do I just connect them all into this one unit that does the texturing for me? No, that's not what I do. Here's what I do. If I have multiple textures, this is going to be my texture unit 0, and it will have this very texture attached to it. And I have, hopefully, more than one texture unit on my GPU, and they will have other textures attached to them. Now, here's a little bit of a point. This is the picture as I will see it as a GPU programmer. When you're writing code from the API's perspective, this is how your GPU looks. The way that your shaders access the textures, this is what it looks from an API perspective. It's as if there are these physical hardware units, however many. But this is the picture that you should see. This is how you should understand your GPU, that it has multiple texture units, multiple physical texture units. But whether or not it actually has those units, I don't care. Because if my GPU doesn't have these units, it will act as if it does. And it will trick me, and it will make me think that it does. So it doesn't matter if it actually physically has these units, right? From our perspective, it will have these multiple units, and I'm going to attach one texture to each one of these units. Now, I should also say that this is just one way of accessing textures on the GPU. There are other ways of accessing texture data on the GPU, which I am not going to talk about. There's more advanced topics, and I'm not going to get into it. But this is a typical way of accessing the textures, and this is the only one that I'm going to talk about. This is the only one that I think you should know. But just want to tell you that there are ways of accessing texture data without going through texture units specifically like this. But they're not important for the context of this course. All right, but so this is the picture that you guys should have in your minds. If I have multiple textures, I'm going to attach one texture to each one of my units, and I'm going to send them separately to my shader. Okay? All right, so let's just take a look at one of them. All right, I have my texture unit 0, and I have my shader over here. So let's see how we can set this up. So this is the whole point of this lecture. We're coming to the core part of this lecture. You ready? All right, tricky part. So let's go through all of the WebGL related code and stuff. First things first. What do? We set the texture data. So this guy, whatever texture data I have, I need to set it. All right, let's do it. Just like the other things we've done, the first thing we're going to have to do will be creating our texture. So GL create texture will create a texture for me, and that's my variable. My text is what I call it here. Basically, this is just going to be some number. Okay, 0, 1, 2, 3, whatever. So that's going to be the name of my texture. Okay, so I'm going to be accessing my texture using this my text variable, whatever I got from WebGL, right? So I created my texture, and the next line, I'm setting the texture data. So when I created my texture, my GPU did not allocate anything. It didn't do anything. It's going to allocate memory when I'm setting the texture data. the way I set the texture data is I first bind the texture by this line. After you bind the texture, everything you do, all the texture calls that you do after that is going to be about this one texture. So I bound this texture. That means that all of the other all the WebGL calls will be about this one texture. And if you want to edit another texture, you need to bind another texture. Right? This is how it works. So by doing so, I don't have to specify with each one of my calls. I don't have to specify which texture I'm talking about. Right? So I set the context by setting bind texture, and then I do this. Now we're going to use bind texture for other things as well. We'll get them in a little bit, but this is how this thing works, right? All right. So I bind a texture, and then the next call is GL text image 2D. That means I'm going to specify a 2D image. All right. I said this is going to be a 2D texture, and next one is 0. That's saying it's going to be bitmap level 0. That means the main resolution. So using this call, I can specify all of my bitmap levels manually, or I can just specify level 0, and then I call this. I say GL generate bitmap, and it will generate all of the bitmap levels automatically. My GPU will generate the bitmap levels automatically for me when I call this. Or if I don't like them, I can just go and say, hey, now bitmap level 1 data is this, and I can specify that. That's an option. So that's why I'm saying I'm setting level 0. Typically that's what we're going to do. We're going to set level 0, and we're going to let our GPU to do the pre-filtering for us and generate all the bitmap levels. The next one, I'm saying that, hey, I would like you to store red, green, and blue values. In this case, it could be RGBA, it could be just red, it could be whatever. There are different things you can choose. I'd recommend that if you're interested, check out the manual for this function to see all sorts of different texture formats that is permitted by WebGL. And then the next one is saying, hey, the image that I'm giving you is in RGB formats, and every pixel, every channel value is going to be an unsigned byte. And here's my texture. Here's my texture data. It could just be an array of RGBA channel values, or it could be just an HTML image tag. The nice thing about WebGL is that you can just give it, hey, there's an image tag here on my web page. Get your data from that image tag, and WebGL will just grab that data, grab the image data from the tag. So that's quite convenient. That's what I prefer doing with WebGL. But you can also directly specify the pixel values as an array. That's an option too. But once you get into that, you kind of need to specify the width and the height of the texture as well. It becomes a little more tricky. So this just makes things a bit easier. All right. So you create your texture, you bind the texture after you create it, and then you set the texture data. Then you say, generate all the bitmap levels. So all the bitmap levels, all the way up to a single pixel, will be automatically created for us by our GPU. We don't have to worry about it, right? However many bitmap levels will be necessary, my GPU will just generate it. All good? Simple enough. So this is all I gotta do to send my texture data to my GPU. So now, after I've done this, my texture exists on the GPU, and it's ready for bitmap filtering, because I created all the bitmap levels by calling this last function. All good. Now, I also need to specify some parameters. I created the data, but I need to tell my GPU how to use that texture, and there are different options for it. For example, I would like to tell my GPU that I would like to use bitmap filtering for this minification filter. So when I'm looking at my texture from far away, and it's like sort of looks smaller and smaller, it's called minification filter. That's going to be, I'm saying, use trilinear filter. This is how you specify trilinear filter in OpenGL and WebGL lingo. Linear bitmap linear. That is, use linear filtering at each bitmap level, and then use linear filtering for interpolating between mipmap levels. Remember, we talked about this last time when we were talking about mipmap filtering and trilinear filtering. There are other options too. I don't have to use this, but this is the typical thing to do if you want to use mipmap filtering. That will give us trilinear filtering. And this is bilinear filtering. That is, if I'm looking at my texture a little too close, like I've zoomed in to a part of my surface such that my pixels are sort of spread apart now, I need to interpolate between them. This is saying use bilinear filtering. So in OpenGL or WebGL, we call it just linear. But this is bilinear filtering when you're zooming in, and this is trilinear filtering with mipmaps when you're looking at your texture from a distance, right? There are various other parameters I can set regarding texture filtering. For example, another thing I can set is the tiling mode. So what do I do in S and T directions? Remember S and T? Yes. In S and T directions, do I want the texture to repeat? Do I want mirrored repeat? Do I want it to clamp to border? I can set it. And for S and T directions, I can set them independently, right? So there are a whole bunch of parameters about texture filtering that I can set. And this is all about setting the texture data and filtering parameters. All right, now that let's say we're done with setting up our texture is ready, it's on the GPU, we set it up, we just want to use it now. Let's get to that part. Let's get to the tricky part. The first thing to do would be taking that texture and connecting it to a particular texture unit. And here's how we're going to do that. Now, first, I am going to pick a texture unit. Okay, I said GL active texture is texture 0. That means I am picking texture unit 0. And then I'm binding this texture. I just bind my texts here. I just want to bind my texture to that particular texture unit. Yeah, so this is a little sort of backwards way of doing this, right? I'm not saying, hey, my text is going to be texture 0. That's not how I say it, and there are historical reasons as to why it looks like this. It's not too complicated, right? You just say active texture is texture 0, and then you bind your texture to that active texture unit. All right, so this is picking the texture unit. Again, this is binding my texture to that unit. Now remember, a few slides before, while we were setting our texture, we also did bind texture there. So this is the other bind texture that I was talking about. So from now on, as long as I'm using texture 0, as long as the active texture is texture unit 0, all of the texture calls that I'm going to be making will be related to this texture. So all of the texture parameter settings, if I change texture parameter settings, everything is going to be about this texture because I did bind this texture to texture unit 0, and texture unit 0 is the active texture unit. So if I want to set another texture with another unit, I just need to change the active texture to another unit and then bind that texture to that unit. Okay? So when I do this, now I have a connection. Now I took my texture data and I connected it to my texture unit. All right. So before we talk about how to connect this texture unit to the shader, let's see what happens in the shader first, and then we're gonna go back and talk about how to connect the texture unit to the shader. Okay. So now we're gonna jump into GLSL because GLSL code is gonna run on my shader, right? So my GLSL code and this shader is going to look like something like this, maybe. So what's going on here? Here I have my texture is this guy, the sampler 2D. That's what GLSL will call the textures. Sampler 2D text is just a 2D texture. And I'm also getting a varying texture coordinate. And then by using the texture 2D function, I will be sampling that texture with that particular texture coordinate. And that this is always going to return an RGBA value. So I can just directly set it to the GLFrag color, and I'm done. If I don't want to do anything else with it, that is. But remember this is always going to return an RGBA value, even if my texture does not store an RGBA value. If my texture doesn't store those channels, you'll get the default values for those channels, whatever the default values are. All right. So here's my uniform sampler 2D and my texture coordinate. So I'm going to set the uniform text sampler 2D, but where is my texture coordinate coming from? It's coming from my previous shader. And my previous shader is going to be, in this case, a vertex shader, right? So from a vertex shader, I send my data to my fragment shader. So let's see what's going on here. My vertex shader is getting two attributes at the top here, and all the way here. It's getting a position and texture coordinate, right? And it's outputting this texture coordinate. It's just passing this, it's getting this attribute and passing it to the rasterizer, and the rasterizer is going to do the interpolation and send the interpolated varying texture coordinate over here. Okay, so texture coordinate sent to my fragment shader over here like this. And yeah, position is just the position, just like we used before. All good? So this is how I'm going to be using textures in my shaders. So the important bit here is this guy. So we know everything else. We know how to connect everything else. The only thing we're not sure about is this guy. So like this is going to be an attribute here in this case, and I'm just assigning it to the varying value text coordinate, and the texture coordinate is sent over here through my rasterizer. The only thing that is sort of unclear that we haven't talked about just yet is how to set this uniform sampler 2D text. Now this, you can think of this as just like any other uniform value. It's going to be a little, the tricky part is there, not difficult, just a little tricky. So yeah, just let's talk about this part only. So how do I set this value, whatever that is, right? So this is going to be very much like setting any other uniform variable on the using WebGL. I'm just going to get the position of that. I call it text, so it's going to be text. I'm just going to get its position, and then I'm going to bind my program. That's using it, and finally I'm going to set its value. Now, what did I do? Now I took its location and I set it to sampler variable here, and I'm setting the sampler to 0. I didn't set it to my texture. Remember, I had my texture. That's not what I did. I set it to 0 because I am using texture unit 0, right? So I am not connecting this sampler to my texture. I am connecting it to my texture unit. That is the tricky part, right? And that's the part that you need to think about. You need to be careful about when you're implementing this. So the important bit here is to make sure that I am setting the sampler to 0, and I'm doing that because I took my texture and I set it to this texture unit 0. All right, so that's the whole complexity of doing this. So of course, if I want to use texture unit 1, I can do that. I just need to activate texture unit 1 and then bind my texture to texture unit 1 by calling this after setting the active texture as texture unit 1. And then I need to do this. I set it to texture unit 1. Okay? In that case, I will be using texture unit 1. Simple enough? If it's texture unit 2, of course it's going to be texture unit 2. It's like whatever it is, let's call it I. Texture unit I need to set this, and I use that. And of course, the obvious question here at this point, well, it just came. Actually, somebody did ask that question. Thank you. Yeah, there's a limit to how many, this I has a limit. So what is that limit? How many texture units can I have? Well, this is going to depend on your GPU. How many units is supported by your GPU? WebGL actually defines a number of these. I have texture 0, texture 1, texture 2, texture 3, whatever. But you can always access texture unit n by saying GL texture 0 plus n. Alright, so these are actually some constants. They're actually integers. Integer constants, and you can add whatever, and that would be your texture unit ID. So you can get a whole lot of IDs beyond what is defined in the API specifically. But quite a few of them are already defined. Probably more than you need. But there's going to be a limit to this, obviously, because I don't have infinitely many physical texture hardware units on my GPU. The limit will depend on your GPU, so you kind of need to ask your GPU. Here's how you do it. So you say, GPU, tell me how many texture units you support. Alright, so I needs to be a value smaller than this maximum. Alright, so that's going to tell you how many units are supported by the GPU that this code is running on. So if you're just using, I don't know, just a couple of textures, you don't need to worry about it. But you set a shader that has, I'm using 3264 textures, maybe you should check that GPU actually supports that. Okay? So, to summarize again, I have my texture, I bind it to my texture unit, and then I set my texture unit and I send it to my fragment shader, and this is how I can access my texture in my fragment shader or possibly my vertex shader. And then GPU will do all of the complicated texture filtering, SE to UV coordinate conversion stuff, all of that complex stuff will be done automatically by the GPU. I won't even need to worry about this. Now, the part that's sort of unclear is, hey, I'm telling my GPU that I'm doing mip-map filtering, and I said I want to do bilinear filtering when I zoom in, I want to do mip-map filtering when I zoom out. Like, how do I tell my GPU to use like which one? Do I need to, am I zooming in, am I zooming out? Like, all of that stuff will be automatically handled by my GPU. You won't have to worry about that at all. So for those of you who are interested, what's going to happen is that my GPU will determine the screen space derivatives of my texture coordinates. The screen space derivatives of my texture coordinates. It's going to numerically calculate them. Actually, the rasterizer will output screen space derivatives of anything you send to your fragment shader. When you're using that data to access the texture, the GPU will have access to the screen space derivatives. And using those screen space derivatives, it will figure out which mip-map level it's supposed to use. And if it is supposed to use anisotropic filtering, and it has to use anisotropic filtering, it will figure out how to do anisotropic filtering for that particular set of screen space derivatives, and it will do the correct anisotropic filtering for you. So all of this complex filtering stuff that goes on, that needs to happen, it will be done by this guy over here, and it will be done completely automatically, and you won't need to worry about it at all. That is if you're rendering something on the GPU. If you have a software renderer, and if you're using textures on your software renderer, then somebody will have to write the actual code to do this. That's going to be more than a few lines of code. But not too complicated stuff, but not terribly easy to implement. Nice thing about this is that we don't have to worry about this. The GPU will take care of all of this complexity for us. So for our project, this is what we will be doing. We'll be sending one texture to our GPU, just like I talked about, and then we will be sampling that texture inside the fragment shader by using the texture coordinates provided by the model. Right? That's all we're going to do, and then we're just going to put that texture on our lovely teapot here, and we'll be done. Well, it doesn't have to be teapot. Like whatever model we're using, we're just going to display that texture on that model. Right, so that's what I plan to talk about today, and this is where I'm going to stop. Do you guys have any questions or comments about this whole process or textures in general? Does this mean when you're running a game, you're limited to a set amount of textures you can have on the screen at once? No, you're not limited to a set number of textures on the screen, but there is a limit to how many textures you can use inside one fragment shader. Remember, you can switch to different programs using different fragment shaders as you're rendering. You render something with one fragment shader, and then you switch to another fragment shader and render something else. You switch to another fragment shader, you render something else. So all of these fragment shaders can use their own set of textures, and they could be completely independent. But each fragment shader will have a limited number of textures if you send them this way. But there are other ways, as I said, there are other ways of accessing textures inside a fragment shader. So that sort of opens up other possibilities of accessing textures. For example, there's this concept of bindless textures on the GPU. So you are able to access textures without explicitly binding them. They're called bindless textures. So there are other things you can do for accessing textures so that you're not necessarily limited to the number of texture units that you're allowed to specify using the connection type that I just talked about. So there are ways to get around it. So the short answer is no, we're not limited, but yes, we're limited if you're going to use it as I explained over here. So you kind of need to access textures slightly differently if you want to use more than that. Another question, what would you use for textures in the vertex shader be? Oh, very good question. So the typical use case for textures is just specifying colors. But textures don't have to be used for specifying colors. You know, when we first started talking about textures, I said textures store information about objects. So that information can be any kind of information. It doesn't have to be color information. And it could be other kind of information. For example, I can store positions inside a texture. And if I'm storing positions inside a texture, I might want to use them in the vertex shader because that's where I do my position related stuff. Like I specify vertex positions in the canonical view space, right? So vertex shader would be the right place to use that kind of textures. But I could also be using colors inside vertex shaders. I can sample a texture to get the color of a vertex, and then I pass it on to my fragment shader. So I could do that as well. And that might be a good idea sometimes because oftentimes I'm going to have a lot more fragments than I have vertices. So if I do texture lookup inside a vertex shader, I will be doing fewer texture lookups. So that might be a good idea. But then again, I'm just going to have interpolated color values in my fragment shader. I'm not going to have independent color values all sampled from the texture inside my fragment shader. So yeah, it's not always a good idea to do that. So that most of the time I'll be using my textures inside my fragment shader, but you know, there are certain cases where it makes sense to access them in the fragment shader and the vertex shader as well. Any other questions? Okay, then I'm ending it here. All right, if there are no more questions, I'm ending it here. All right, well, good luck with the rest of the project, and I'll see you all next time. Yeah, thank you.